everyone. So we are continuing to solve our exercise 1.1 of real numbers from NCERT book, and we have done first and third question in our previous video. So in this video we are going to do rest second, fourth and fifth question. So second question says, show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5 where q is some integer. So here let a be any positive integer and b is equal to 6. Then by applying Euclid's division lemma, we have a is equal to 6q plus r. Okay, and here q is some positive integer and r is equal to, here r is greater than or equal to 0 and less than 6. So r is equal to 0, 1, 2, 3, 4 or 5. On substituting r, we get, if r is equal to 0, a is equal to 6q or equal to 2 into 3q. If r is equal to 1, then a is equal to 6q plus 1. Nothing common. If r is equal to 2, then a is equal to 6q plus 2, or take 2 common and write down as 3q plus 1. If r is equal to 3, then a is equal to 6q plus 3. Here 3 will be common, not 2. Then if r is equal to 4, then a is equal to 6q plus 4. This is equal to 2 common here, 3q plus 2. Then if r is equal to 5, then a is equal to 6q plus 5. Nothing is common. So we see clearly that if a is equal to 6q or 6q plus 2 or 6q plus 4, then a is an even integer. And if a is equal to 6q plus 1 or 6q plus 3 or 6q plus 5, then a is an odd integer, as an integer can be odd or even, hence shown. Now question number 4, it says, use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. So now here let a be any positive integer and b is equal to 3. Now applying Euclid's division lemma, we have a is equal to 3q plus r, where r is greater than or equal to 0 and less than 3, where q is some positive integer and r will be equal to 0, 1 or 2. Now substituting r, we get a is equal to 3q or a is equal to 3q plus 1, or a is equal to 3q plus 2. So now squaring on both sides, we get a square is equal to 9q square. So this I can write down as 3 into 3q square. So a square is equal to 3m, where m is equal to 3q square. Now in second case, a square is equal to 3q plus 1 square. So this is the first case. Now this is second case. This I can write down as 9q square plus 6q plus 1. I can take 3 common in first two terms. So I get 3 square plus 2q plus 1. Now this I can write down as 3m plus 1, where m is equal to 3q square plus 2q. Now in third case, a square is equal to 3q plus 2 whole square. This is 9q square plus 12q plus 4, and this I can write down as
9q square
12q plus 3 plus 1, because I can take common 3 now. So 3q square plus 4q plus 1 and plus 1 outside. This I can write down as 3m plus 1, and where m is equal to 3q square plus 4q plus 1. The square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. So, hence shown. So let's move to question number 5, the last question of this exercise. It says, use Euclid's division lemma to show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. So here also let's take, let a be any positive integer and b is equal to 3. Now applying Euclid's division lemma, we have a is equal to 3q plus r, where q is some positive integer and r is equal to, here r will be greater than or equal to 0 and less than 3. So it will be 0, 1 or 2. Substituting r, we get a is equal to 3q, a is equal to 3q plus 1, or we have a is equal to 3q plus 2. Cubing on both sides, we have a cube is equal to 27q cube. This can be written as 9 into 3q cube, or I can write down this as 9m, where m is equal to 3q cube. So this was first case. Now let's take the second case. A cube is equal to 3q plus 1 whole cube. So a plus b cube is a cube plus b cube plus 3 into ab into a plus b. So we get 27q cube plus 27q square plus 9q plus 1. Now in these three terms I have 9 common, so I can write down as 9 and 3q cube plus 3q square plus q and plus 1. So this can be written as 9m plus 1, where m is equal to 3q cube plus 3q square plus q. In the third case, a cube is equal to 3q plus 2 whole cube. For the cube, we get 27q cube plus 8 plus 3 into 3q into 2 and 3q plus 2. We get this as 27q cube plus 54q square plus 36q and plus 8. So here we can take again 9 common. So 3q cube plus 6q square plus 4q plus 8. So this I can write down as 9m plus 8, where m is equal to 3q cube plus 6q square plus 4q. Therefore, we can say the cube of any positive integer is of the form 9m plus 1 or 9m plus 8. Hence, shown. So we have finished exercise 1.1, and in the next video we'll talk about the concept of fundamental theorem of arithmetic. So stay tuned and see you all.